Section 6.2 talks about the behavior of polynomial functions. So we primarily touched on polynomials in the last section, but we really spent our focus on quadratics. But now we can work with polynomials of any degree and an inflection point and concavity. So inflection points occur where there is a change in concavity, and we can identify inflection points by finding the location of the steepest slope, right, or the largest ARC magnitude. So when we get to where we're looking at the ARC a little bit later in the review, you'll notice that I want to choose the largest value. It doesn't matter the sign of the number, but the biggest in numerical value. There's always an inflection point somewhere between a maximum and a minimum. So if you find a maximum and a minimum on a graph, then somewhere between those points, the concavity had to change and create an inflection point. On a cubic function, the inflection point occurs halfway between the two turning points if they exist, and you can compute the location by averaging their respective x values. Once you identify an interval in which an inflection point occurs, you can find it on the calculator by doing the following. So this is where we find the ARC value and then we look for the biggest possible one. So let's actually apply this to an example. So here we have a quartic function, and we call it a quartic function because it is of degree 4. So the first thing it wants us to do is find all the x-intercepts. So I need to start out by plotting this function in my calculator. So it is negative 12x to the 4th plus 61x cubed plus 525x squared minus 1001x minus 4989. And I'm going to zoom fit just to give me some kind of idea of where to start in terms of my window. So we can see it looks like it's crossing 1, 2, 3, 4 times. It's a little hard to see what's going on around the x-axis, so I'm going to go in and adjust these y values. The x values look fine. So this is going all the way up to, this is going all the way down to like negative 123,000. I think that's a bit extreme, so we'll take it down to like negative, let's say 6,000. And then it stopped at 6,000, but I could barely see the top of that, so I'm going to take that up to, actually I'm going to take that down. I will take it up to 10,000, see what it looks like. I can always adjust it if I don't like it. So the function comes up, we can see it cross the x-axis twice there, and we can see it cross the x-axis twice there. So now we have a little bit better picture of our 1, 2, 3, 4 zeros. So the first thing I have to do is I have to kind of put a range in for the zeros. So I want to find this first one here. So this graph I think is like negative 10 to 10, so I can kind of see it's 1, 2, 3, 4, 5. It's somewhere between 4 and 5. So I'm going to second calculate 0. The left bound I'm going to say negative 5. And I'm going to, the right bound I'm going to say negative 4. And it's going to guess, and there it is. So if I didn't pick an interval with a 0 in it, it would actually give me an error. So it's not ever going to return a wrong value. All the values will be zeros. So the first 0 occurs at x equals negative 4.34. So now we got to find the next one. So since I cut this off at negative 4, and it looks like it crosses again somewhere before 0, I'm going to use negative 4 and 0 as my bounds. So negative 4, 0, and I get the second 0 at negative 2.91. My other two zeros are positive, and so I'm going to start at 0 and I'm going to chop it off somewhere in here, so I'm going to just say like 7. So second, calculate 0. We'll start at x equals 0. We'll stop at x equals 7. Yep, and that's nice. Like I can see here, I did grab in between. And we get a 0 at 3.92. Now we got to grab this last guy. So second, calculate 0. I'm going to start at 7 and go all the way to 10. And this is at 8.4. So these are all 4 of the zeros. Now, one thing to keep in mind, it doesn't have to be the case, but since this was a degree 4, that means there will be, let's not use the word maximum, not to confuse you, at most 4 zeros. So they don't always have to have 4, but you'll never have more than 4 because it's degree 4 polynomial. So we want to find all the local maximum and minimum points. So if we go back to the picture, the local maxes and mins are these like turning points in the graph. So we want to figure out where these occur. So if I try to calculate the maximum, it's going to let me do bounds. So I can actually grab these individually. So we know this 0 is at negative 0.434. So I'm going to start this back at negative 5. And I'm going to stop at 0 because that'll grab me this guy. Oops. And notice here in the question, it says points, so we want to give the x and y coordinate. So there is a maximum at negative 3.68, comma 563.69. There's a second maximum right over here. So we're going to go to second, calc, oops, maximum. So I'm going to take the left bound as 3 and the right bound is 10. And we get another one at 6.64. Comma 6,042.77. Now there's also going to be a local minimum because this graph has to turn again, right, to get back up here. So we're going to go to second, calc, minimum. And I'm going to grab, let's say, negative 2 over to positive 2 should get it done. And we have a minimum at 0.85 and a y value of negative 5429.35. So if I do a little sketch here, right, my function looked like this. So there was a local max, there was a local max, there was a local min, and in between these maxes and mins, I should have an inflection point occur in there. So we want to determine the domain and range of this function. So the domain of any polynomial is all real numbers. But the range for this one is actually not too bad. So we can see that the graph's going down to negative infinity. So if I'm reading it from the bottom to the top, right, we start at negative infinity for the y values. But this maximum right here, it was very clear on our picture, was the biggest point on the whole graph, and its y value is right there. So I also could have just done second max and put negative 10 to 10 in, and it still would have returned that value. So sometimes if you conceptually know how these answers work together, it can help you answer other things very quickly. If we want to find the intervals where the function is increasing or decreasing, well, once we found our turning points, we've actually got all the information we need. So the function right? It does a lot of increasing and then decreasing. So I'm going to read this from left to right. So when x is negative infinity, all the way to this first maximum, which was negative 3.68, the function's increasing. Then at negative 3.68 down to here, it's decreasing. So I'm going to pick it up with negative 3.68, and the x coordinate of that point is my minimum right here of 0.85. Then at 0.85, it increases until it gets to this turning point. So at 0.85, we increase all the way to this x value, which was our second maximum of 6.64. Then from that point all the way to infinity, it's decreasing again. So this little symbol isn't really necessary in y'all's class. It's called union. We usually use it in between intervals, but I've seen in the past where you can just get away with parentheses is fine. E says approximate the x coordinates of all the inflection points to one decimal place. So this is where we're going to have to look at our ARC, or the average rate of change. So if we come back up here, right, here's the instructions for doing this, if you've forgotten. So we've already done the first step. We have our function in y1. Now I need to go into my lists. So I'm just going to hit Stat, Edit, go up to L1, and in L1 I have to put the following commands: sequence, XX, A to B, delta T. So the first interval that I'm going to pick, right, because I'm going to have an A and B, I know where the first inflection point occurs. It occurs between these 2 points right here. So my first inflection point, I'm going to use the interval negative 3.68 or negative 3.6 because we want to go to one decimal place to 0.8 because we know it's between this x value and this x value. So I have to do sequence. So I'm going to go to Stat, Calculate, second stat, Ops, their sequence. And I'm going to enter x for the function I want to use, x for the variable, then my A and B, negative 3.6 to 0.8, that's where it starts and stops. And then, because I want to do this for one decimal place, my delta t is going to be 0.1 because I want it to check every tenth of a point. So then I'm going to hit enter, and so now you can see my x values. It starts at negative 3.6, 3.5, 3.4. It's counting up by 0.1. Then in L2, we want to plug all those values into the function. So we're going to go to vars, y variable, function, there's y1. And remember, I can go to second 1 to choose L1. So now it's plugged all those values from over here into my function. L3 says find the change in y over x. So it's finding the average rate of change, right? So if I go to second stat ops, just below sequence right here, I see delta list. So I want to do the change in L2, second 2, right, divided by, I got to come back to this menu again to grab delta list again, over the change in L1. So now everything in list 3 are my ARCs. So I want to scroll until I find the absolute biggest number. So what's happening here is if we go down, we can see that these y values are climbing, right? Even though they're negative, they're getting bigger, and it's the magnitude I care about. So they're getting bigger and bigger and bigger and bigger, bigger, bigger. Keep going down, and then suddenly they start falling again. So if we look right here, we go 2013, 2020, and then suddenly it falls by 1, right? And then starts dropping. So 2020 is the largest value. And if I scroll left, there is the x coordinate that it occurs at, negative 1.8. Then I need to find my second inflection point, and I know it occurs between these values. So for the second one, the interval that we're going to choose is going to be 0.8. We're going to start right where we left off, and we're going to go up to 6.6. So once again, I'm going to have to start over here with my lists. So I'm going to clear. All right, so now sequence, so second stat, ops, sequence, x, comma, 0.8, comma, 6.6, comma, 0.1. Perfect. So then in L2, we're going to go to vars, y variable function, y1, and now we're going to plug all those new values into our function. And then in L3, second stat, ops, and we're going to grab delta list. So I want the change in y values divided by the change in x values. So these are my ARCs. So once again, we'll scroll. We see they're getting bigger, right? Well, bigger, 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 bigger. Just kind of looking at the first digit, so 3. And there's the drop. So 3077, 3081, and then it drops down to 3077. So if we scroll over here, 4.2 is the x coordinate. Of the second. Right, so now it wants us to discuss the concavity. So this is where this sketch can come into play. So we can see here the graph is concave down until you get to your inflection point, and then it's going to change. So the graph is concave down from -infinity to -1.8 because that was the x-coordinate of that point. Then it changes concavity and it's concave up till it gets to the next inflection point. So it starts at -1.8 and it's concave up till it gets to 4.2. So in between these 2 points. Then from this point all the way to infinity, it's concave down again.